Okay, my research primarily focuses on the advanced design for reliable and sustainable structures under extreme loading conditions, with the aim of improving the structure's safety, reliability, and sustainability. So to achieve this goal, my research develops along these four directions: outplane stability design of structures, fire performance of structures, seismic behavior and the resilience of beam column connections. And recently, I've also started to work the explosion response of urban underground infrastructure. And today I'm going to present our research on the advanced design method for steel and stainless steel structures at both room temperature and elevated temperatures. So this is today's topic. And now let's start from the background. Let's see how and why the advanced design method was developed. Okay, in conventional steel member design, such as this beam, we usually need to check two aspects: the cross-section strength, which is governed by local buckling behavior, and the member stability, which is more related to the global buckling behavior. In practice, there are two design approaches. The simplified design method, which is often referred to as the hand calculation approach, and the advanced design method based on numerical analysis. In conventional design standards such as Eurocode, the simplified design method usually relies on the cross-section classification concept. Based on the weight to thickness ratio of the most critical plate element in the cross-section, the cross-section can be classified into different classes. And for these different classes, we use plastic, elastic, or effective resistance as their design cross-sectional resistance based on plastic, elastic, or effective stress distributions. And after determining the design cross-sectional resistance, the design member resistance is obtained by multiplying the design cross-section resistance by the global buckling reduction factor to account for the global buckling behavior. So this is how we could apply the simplified design method for steel member design. And another option is advanced design method based on numerical analysis. In recent years, the numerical methods are becoming more and more popular in practical structural design. And owing to the high computational efficiency, beam finite element models are very popular by designers. And in the beam finite element models, the global buckling behavior could be directly captured in beam finite element analysis. But beam FE models, they cannot represent the cross-sectional local buckling behavior. So a very natural question is, can we just combine the beam finite element analysis and the traditional cross-section classification concept? However, when we look more closely at the cross-section classification concept, we'll find some limitations. For example, according to the cross-section classification concept, the design resistance is limited by yield strength. So for stocky cross-sections, we can see here, the string hardening effect cannot be considered in the design for stocky cross-sections. And also these artificial steps, leads to a discontinuous treatment of the local buckling effects, which doesn't reflect the real structure behavior. And for class 3 cross-sections, we use elastic section resistance, so the partial plasticity is not exploited. And finally, also the most important is this concept is based on the weight to thickness ratio of the most critical individual plate element in the cross-section. However, during local buckling, the most critical element may be supported by adjacent plate elements, but this beneficial effect from the plate element interaction cannot be taken into consideration in this concept. So to overcome the limitations of traditional cross-section classification concept, recently, the continuous strength method, CSM, was developed. as an alternative to the cross-section classification concept. This is a deformation-based approach. The CSM base curve defines the maximum strain that a cross-section can experience prior to its failure. So stocky cross-sections have higher strain limits, and the determined CSM strain limit for the slender cross-sections are relatively lower. And the CSM strain limit is taken as a multiple of yield strain. So here we can see that the CSM base curve allows for a continuous treatment of local buckling effects across stocky cross-sections and slender cross-sections. This is a difference between the CSM base curve and the traditional cross-section classification concept. And also the CSM strain limit is determined based on the cross-section slenderness lambda p, which is calculated using the elastic local buckling stress of the full cross-section, not only based on the most critical individual plate element. Therefore, the beneficial effect from the plate element interaction could be naturally accounted for in the CSM base curve. And for stocky cross-sections, the CSM strain limit is taken as even up to 15 times of yield strain. So for stocky cross-sections, the yield strain could be exploited. And based on this continuous strength method, CSM, recently the advanced design method has been developed, combining both the beam finite element analysis and the continuous strength method. So in the application of the advanced design method, first we need to use the beam finite element models to perform geometrically and materially nonlinear analysis with imperfections, GMNIA, to directly capture the global buckling behavior. At the same time, the strain limits obtained from the continuous strength method, CSM strain limits, are introduced to account for the local buckling behavior. So during the loading process of the beam finite element analysis, either the CSM strain limit, which is governed by local buckling behavior, or the peak load, which is more related to the global buckling effect, whichever is reached first will determine the failure mode and the design member resistance. This is the application of the advanced design method. So now let's look at the first issue addressed in our study, that is the imperfection. So now let's move on to this topic, how we developed the equivalent geometric imperfections applied in this design method. So here I represent the imperfection. And in beam finite element models, for modeling convenience, residual stresses are typically not explicitly introduced into beam FE models. And instead, the equivalent geometric imperfections, which consider the combined influence of both geometric imperfections and the residual stresses together, are introduced into the beam FE models. And our study aimed to develop the equivalent geometric imperfections for use in GMNIA for the outplane stability design, which is a quite common failure mode in metallic structures, with a particular focus on the lateral torsion buckling. So in parametric studies, to obtain the required equivalent geometric imperfections, first we need to perform GMNIA with both geometric imperfections and the residual stresses together to obtain the benchmark data of the design member resistances as presented by the black curve. And secondly, we need to iteratively run the beam FE models with varying geometric imperfections only without residual stresses. We need to iteratively run the beam FE models with varying geometric imperfections from the blue curve to the red curve until the ultimate resistance coincides with the benchmark data. The imperfection amplitude at that point was taken as the required equivalent geometric imperfection. So in this way, finally, through parametric studies, we obtained the required equivalent geometric imperfections for a series of cases. Here, I just show some examples. And then to account for the different residual stresses, residual stress influence in various cross sections. Here we can see that to consider these different residual stress effects in different cross sections, we proposed to incorporate the minor axis flexural buckling the minor axis flexural buckling imperfection factor alpha z, which can be obtained from the Eurocode, into the determination of the proposed equivalent geometric imperfection. And then after normalized by alpha z, these numerically generated required equivalent geometric imperfections could be converted into the numerical results of beta values. Beta is the reference relative imperfection. And based on these numerical beta values, finally, we proposed two formats of the beta values. So based on these numerical beta results, finally, we recommended the beta values to determine the equivalent geometric imperfection. Here, we proposed two formats of the equivalent geometric imperfections. One option is the equivalent geometric imperfection could be applied following the shape of the lateral torsional buckling Adam mode, which is more accurate. But in the first option, we need to perform linear buckling analysis first to obtain the lateral torsional buckling Adam mode. So we proposed the second option, which is more convenient, where we don't need to perform linear buckling analysis in advance. And in the second option, the equivalent geometric imperfection could be applied directly as lateral bow imperfections, a combination of a full half sine wave curve and a full sine wave curve to cover different bending moment gradients. So the second option is more convenient. And here I show the comparisons between the design member resistance predictions obtained from the GMNIA, employing the proposed equivalent geometric imperfection following the lateral torsional buckling Adam mode, the first option. And this figure presents the ultimate resistance predictions obtained from the hand calculation approach given in Eurocode. Both were normalized by the benchmark FE beta. So the ratio equal to 1 means accurate member resistance prediction, and below 1 means safe predictions. So here we can see that compared with the hand calculation approach, employing the proposed equivalent geometric imperfection in GMNIA provides more accurate and consistent member resistance predictions. Also, it could eliminate some unsafe predictions. We also look at other steel and stainless steel members under different loading conditions. And generally, compared with the hand calculation approach given in Eurocode, employing the proposed two formats of equivalent geometric imperfections in GMNIA could provide more accurate and consistent member resistance predictions. The proposed two formats of equivalent geometric imperfections have been included in Eurocode 3 Part 114, Design Assisted by Finite Element Analysis. Okay, after resolving the issue of imperfection, now let's look at the second issue we addressed in the application of the advanced design method. That is the limitation of strain limit. So the original CSM strain limits were developed only considering normal strains without considering any shear stresses. So for pure compression or pure bending cases, there is no problem, because we could only consider the normal stresses and strains. But how should we consider these shear effects on the cross-section resistance? And particularly in lateral torsional buckling cases, there is internal second-order torsion developing within the cross-section, including centimeter torsion and warping torsion, leading to corresponding the normal stresses and the shear stresses. Here we can see. And this, the normal strains, including these warping normal strains, no problem, could be directly extracted from beam finite element models and checked against the original CSM strain limits. But the treatment of these shear effects is less straightforward. And also, how should we consider the interaction between bending, shear, and torsion? That is the problem. So in our study, we followed these two steps to address this issue. First, we will investigate the interaction between shear and torsion, only considering the combined shear effects without any normal stresses or strains, only considering the shear effects. And next, we will look at the interaction between bending and the combined shear effects due to both shear forces and torsion. Okay, so first let's look at the combined shear effects due to shear force and torsion. These are the shear stress distributions in different cross sections under vertical or lateral shear forces and torsion. And based on these shear stress distributions, we proposed the shear utilization factors, eta y and eta z, to consider the combined shear effects for major axis bending cases or minor axis bending cases. And the shear utilization factor, eta, is taken as the shear force divided by the torsion-reduced shear resistance, thereby considering the combined shear effects. So through these proposed shear utilization factors in the application of the advanced design method, we could consider the combined shear effects due to both shear forces and torsion. These proposed shear utilization factors to consider the combined shear effects have been incorporated into the Eurocode 3 Part 114, design assisted by finite element analysis, and also the American Design Standard AISC 370, designed for structural stainless steel buildings. And the next step is to consider the interaction between bending and the combined shear effects due to both shear forces and torsion. So here, according to Eurocode, to consider the adverse effect from the high shear forces on the design bending resistances, we need to use the shear reduced yield strength to replace the original yield strength based on these reduction factors. So in the steel member design, to consider the shear effect, according to Eurocode, we should use this shear reduced yield strength to determine the cross-sectional bending resistance. And here in our study, we followed the similar philosophy and adopted the consistent formats. We proposed this expression, the top equation, to reduce the original CSM strain limit based on these reduction factors, rho y and rho z. And these reduction factors, they are calculated using the proposed shear utilization factors, eta, to consider the combined shear effects due to both shear forces and torsion. Therefore, from the through the top equation, we could reduce the original CSM strain limit and consider the interaction between bending, shear, and torsion. So the underlying mechanism behind this equation is with increasing shear utilization ratios, the reduction factor rho will increase from 0 to 1. Then the CSM strain limit will progressively reduce and reduce until finally the shear area is fully utilized by shear, but the remaining area within the cross-section still can provide bending resistance. So this is the underlying mechanism behind this equation. And this proposed equation to reduce the CSM strain limit, as well as these expressions for the reduction factors, have been included in the Eurocode and American Design Standard. So next, we applied the advanced design method employing the proposed shear-reduced CSM strain limit. And then we obtained the member resistance predictions as presented by these red markers. And the blue markers, they are corresponding to the hand calculation results following the equations given in Eurocode. So here it's obvious that the hand calculation approach sometimes is very conservative, but our advanced design method consistently provides more accurate member resistance predictions. We also looked at other loading conditions and other cross sections, and generally compared with the hand calculation approach, the proposed advanced design method provides more accurate and consistent member resistance predictions. Okay, as conclusion for the advanced design method at room temperature, to overcome the limitations of traditional design method, the advanced design method has been developed. And our study extended the advanced design method for the first time to the outplane stability design, enabling it applicable to three-dimensional structures. And compared with the traditional hand calculation approach, the advanced design method provides more accurate and consistent member resistance predictions, which further indicates more material saving, cost-effective, and more sustainable structure design. Additionally, this design method also streamlines the design process by eliminating the need for cross-section classification, the calculation of effective section properties, and the calculation of effective member length, thereby promoting more practical structure design. Okay, next, this advanced design method also has been extended to elevated temperature structure design. In metal structures, we know that fire result in the significant material degradation, such as the significant reduction in stiffness or strength for carbon steel or for stainless steel. And these material degradation effects, as well as those indirect fire actions, are relatively difficult to address through the hand calculation approach. However, when we apply the advanced design method, we could consider these more complex scenarios. For example, in our study, we verified the elevated temperature advanced design method for these unrestrained members or these under-restrained members, such as these members with axial restraints or with axial and rotational under restraints. And these under restraints, they are used to simulate the support provided by the adjacent elements in fire. So the advanced design method could be applied to design these more complex scenarios. Here first, in our study, we extended the room temperature CSM base curve to elevated temperature CSM base curve. And similarly, in the fire design, here, either the CSM strain limit, the elevated temperature CSM strain limit, or the critical temperature, whichever is reached first will determine the failure mode and the failure temperature of the member in fire. So similar to the application of the room temperature advanced design method. And these two figures, they present the comparisons between the predicted failure time obtained from the elevated temperature advanced design method and obtained from the hand calculation approach given in Eurocode 3 Part 1, 2. So here we can see that compared with the hand calculation approach, the elevated temperature advanced design method, it's obvious that the elevated temperature advanced design method provides more accurate and consistent the failure temperature predictions. And also, more importantly, we can see that the application of the elevated temperature advanced design method could be helpful to reduce these unsafe predictions. That is more important. The reason is because the it's relatively more difficult for hand calculation approach to consider those indirect fire actions, such as the additional compression. For example, in this unrestrained member, there would be additional compression due to the restrained thermal expansion. However, this indirect fire action is not easy to adjust through the hand calculation approach, whereas the advanced design method could directly capture this material degradation and these indirect fire actions. Okay, we also look at the non-uniform heating cases, such as this one-side heated column. And something interesting is different with the room temperature design. We know that for room temperature design, due to instability, the critical location typically appears at the compressive side. However, if we look at this non-uniform heating case, probably the failure, the critical location will appear at the compressive side. But if we look at this column, on the heated side, there would be more significant the material degradation. So probably the critical location also occur at the heated side. So this is also a difference between the room temperature design and the fire design. So here we verified the advanced design method for these non-uniform heated columns. And we can see that the predicted failure time as presented by these blue boxes, they are generally close to the benchmark FE data, these black circles. We also investigated the application of the advanced design method for the stainless steel frames. And similarly, the predicted failure time generally align very well with the benchmark data, these black circles. So we also look at these non-uniform heating cases and the frames. And so as a conclusion, our study extended the advanced design method to fire scenarios, making it applicable to more complex cases like those unrestrained members and those non-uniform heating cases. And compared with the hand calculation approach given in Eurocode, generally the elevated temperature advanced design method could provide more accurate and safe predictions. Also similar to the room temperature design, the elevated temperature advanced design method also streamlines the design procedure, which indicates this design method promotes both more sustainable and practical structure design. Okay, finally, in the end, I will give a brief introduction to some of my other studies. In addition to this advanced design method, I would be very happy to discuss any potential collaboration opportunities. So in the first direction, the outplane stability design, in addition to the development of the advanced design method, I also proposed the simplified design method, the hand calculation equation for stainless steel beam columns. The proposed equations have been included in Eurocode 3 Part 1.4. And in terms of the fire performance of structures, I also carried out the elevated temperature material testing on 4 novel stainless steel material grades, and also developed the elevated temperature material models, which can be directly used in structure fire design. For stainless steel cross-sections, members, and frames, we developed the both simplified design method and advanced design method. Some proposals have been included in Eurocode 3 Part 1.2. Additionally, we'll be also starting to work on the design of hybrid steel and stainless steel beam column connections in fire, and the component-based method in Eurocode 3 Part 1.8 could be extended to fire scenarios. And recently, I've also started to work on the machine learning aided design of aluminum alloy members in fire to improve both accuracy and efficiency of structure fire design. And I've also investigated the seismic behavior and the resilience of beam column connections. For example, I carried out the cyclic testing and the numerical analysis on steel concrete, the composite beam column connections, which have been implemented in Tianjin City and Financial Center. And to improve the resilience and sustainability of beam column connections, I've also developed the replaceable beam column connections and the self-centering beam column connections assembled with the shape memory alloy ring spring systems to facilitate rapid and cost-effective post-seismic repairs. And recently, I've also started to work on the dynamic response of utility tunnel under explosion shock waves. Okay, so that's all. Thank you for your attention, and I would be very happy to take any questions and discuss.